Hi everyone, my name is Alex. I'm an engineer and my passion is design, development and prototype production of all sorts of engineering solutions. Yes, I know, I've been absent from YouTube for quite a while now, but it's not that I'm dead or something. It's just that I was so busy with several customer projects, of which unfortunately I cannot show anything here on YouTube, that I didn't have the time to make any new videos. But I'm back, at least with this one. So, over New Year's I became sick and I had to spend a few days in bed. And after I got a little better, I felt like working out a few design ideas for a tool that I had in my mind for quite some time now. A tool, actually this tool here, and what it is a portable and universal hardness testing tool. Now, this tool here is inspired by two patents for a portable hardness tester that was built back in World War II by a German aviation company. And then there is a second patent from an American from the late 50s or early 60s, I think, which differed only in minute details from the German patent. However, I do not know if the American version was built or made. Maybe you can comment on this if you know something. These tools, they look quite similar to the one I made. Particularly here, the steer mechanism for clamping the sample or clamping the workpiece. However, up here, all this stuff that is used for testing, this tool here differs in a few or many aspects from the things in the patent. I assume from studying the patents that these tools must have been a little tedious to use, the historic ones. And so I came up with this design which suits my taste for a portable tool here. Now, you may say, Alex, that's stupid. Why would you build your own hardness testing tool if they are available from the market? Not the historic ones are, but modern hardness testing tools are available from the market. Now, you see, there are three groups of hardness testing tools on the market. The one is the big stationary machines, big expenses, big mass, not portable, cannot be used on the job or in the field, and to be used with samples or small parts. That's no good for me, for the work I do at least. Then there's the mostly electronic testing devices, which are like a pencil that you push onto the workpiece, and it measures the hardness with an indenter and with tiny forces. But that's also a solution that is really not good for me, because it doesn't work in the standardized ISO method. It's an approximated method with tiny forces, and consequently the scatter of the results is really large. So I don't like these electronic tools. Also, you know how it is, if you use an electronic tool only occasionally, several projects may come up, like the dead batteries and what have you. So for the kind of work I do, this wouldn't be a good solution to invest in. And then there are the purely mechanical hardness testing devices. There are some suppliers on the market for those, but what I don't like in these tools on the market is they usually come only equipped for one hardness testing method. So if you buy a Rockwell cone hardness tester, you can only do Rockwell cone hardness tests with those. If you want to do something else like Vickers hardness testing, you have to buy a new or an additional calibrated spring and indenter combination from them. And that's also something I don't like in a tool. The nature of the work I do requires my equipment and my tooling to be as universal as possible by any means. And that's something I value in this design here very much. So now you may say, Alex, what the heck? What is it with you and hardness? And so, are you a snob in this regard or what? Which Stefan Gotteswinter actually called me. So, and he also suggested I make this video. So thanks, Stefan. Well, anyway, why is hardness testing so important for me? Well, let's say you fabricate a welded aluminum part, and it has to be a durable part with that is under fatigue load or dynamic load, and it has to have good strength. Now, if you use aluminum as welded, then it's essentially annealed and soft as butter compared to other metals. So let's say you have to do a heat treatment to precipitation harden the aluminum part again. How do you know that your heat treatment worked out well? How do you know that the quenching worked out well? How do you know that the aging worked out well? How do you know that the aging time was sufficient? You only know it if you can measure the material strength, and the material strength is related to the material hardness. So the harder a material, the more strength it got. With the Brinell and the Vickers hardness testing methods, which can be done with this tester here, there is even a direct proportion between hardness and strength. With Rockwell cone and Rockwell ball method, which can also be done with this tester here, there is a non-linear relation, but that doesn't matter. With the aid of available tables, you can convert hardness to strength of a material. So strictly speaking, you can only make a qualified statement of material strength if you cut a tension test sample from the part. But in an approximative way, you can do it with hardness testing and convert the hardness reading into a material strength. So this is something that's very valuable if you are confronted with questions like, Alex, this part here broke. Was the loading too high or was the material too weak? So this is something that you can make a qualified statement on if you have something at hand, or at least a reading for the material strength. Of course, also quality control. If you have to make sure that a part has a certain strength that you get delivered from a supplier, then you can check if he actually did use the right material for you. And lastly, there is another application for hardness testing to very roughly grade materials. Let's say you have a mixed up material bin where you have quench and heat treated tool steel and some mild steel, and it unfortunately got mixed up. So with hardness testing you can very quickly sort this out. You cannot sort out between alloys of the same strength, but at least you can roughly sort it out. If you only have two alloys in stock, for example, then this is a very handy method. So enough talk now, and let's see what this tool can do. With all hardness testing definitions, there is a certain similarity. And these methods, they require that an indenter, which may look like this one and which may have a tip shape, or it may be a cone, a pyramid or a ball, it requires that this indenter is forced as perpendicularly as possible into the workpiece or sample surface with a defined force, that is. And then we either measure how deep it sinks into the surface, which is true for the Rockwell methods, or we measure the size of the indent, which is true for the Vickers and the Brinell methods. Now, let's get an overview of the tool and see how this is done here. Now, the indenter sits in the front here. So how does the tool work? Well, the workpiece or sample is clamped in between these two jaws here, or if you have a very big workpiece, then you clamp the tool onto the workpiece, but also with these two jaws here. The jaws are opened and closed with these gears. So you see we have gear nuts here on these two threaded rods, and the central gear operates these two nuts synchronously and makes possible that these two jaws move in a parallel fashion and allow clamping of the workpiece. Then here is obviously the spot where the indenter works and where the measuring takes place. And the indenter sits in this beam and shell mechanism, which you can see it has a limited travel of so much. So how do we create a defined force with which the indenter is pushed into the surface? This is done with this thumb screw in the back here, and this thumb screw pushes onto a calibrated bending beam that is in here, and this pushes the indenter onto the surface. And we read the amount of the force that we push the indenter onto the surface with the aid of this dial indicator here. Now this is already calibrated in combination with this bending bar in here, and therefore we do not read a length anymore with this dial indicator, but rather we read directly the force in kiloponds. Now, not to be confused with kilopounds, but this kilopond is the historic unit in the metric system for force. 1 kilopond is the gravitational force of 1 kilogram on Earth's surface. So essentially 1 kilopond is 9.81 newtons. I have kiloponds here, even though it is not used anymore, because the definition for all the hardness testing methods is done historically in kiloponds, so we have round kilopond numbers. Now the current ISO standards, they have 1400 and something point something newtons, but I'd rather work in round numbers, which is why we have the kiloponds here. For Rockwell, for example, we use 150 kiloponds testing load, and for the other tests we use either 10 kiloponds, 50 kiloponds, depending on which method you're using. So this allows us to force the indenter into the workpiece with a certain force. Then the second indicator here is used only for the Rockwell tests, and it measures how deep the indenter sinks into the surface. So this is also directly calibrated in this sticker via this sticker ring here to directly read Rockwell cone and Rockwell ball units. And you zero this, I'll show it when we do the tests with the aid of this thumb screw here, once the preload is applied. But I'll show that in a second. So essentially that's all that is to the tool. Earlier I already mentioned that these dial indicators are calibrated. So what does that mean? Calibration, the word, only describes that you compare the results that you achieve with your tool with a known standard. Then you know if your results are good or not, and you also know how far away from the theoretical ideal value or ideal result you are. And in hardness testing you can achieve this with such hardness comparison plates. These are, you can buy these. This one, for example, here is rated 54.7 HRC, that means hardness Rockwell cone. So with the Rockwell cone test method we should ideally get the result 54.7, and in reality we have plus or minus a certain error that the instrument has, that the way you conduct the experiment has, and so on. So let's see how that works. I already have put in the HRC indenter, so we will push in this indenter into the workpiece with a certain preload. Then we will zero the depth indicator. Then we put in the main load of 150 kiloponds. Then we release that load, go back to the preload again, and measure how much deeper the indenter now is after we applied the test load. So let's see how that goes. I'll try to stay in frame, but that may not be as easy. Something to note here, you see I've put in already quite some indents in this test plate or in this comparison plate. Something that's important is to stay away a certain distance from older indents so as not to be influenced by the hardening that the older indents created in the material, and only to test virgin material. So a rule of thumb says to stay away at least 5 times the diameter of the indent, and I'll try to do that. So first thing, we clamp the sample. Let me see. Yeah, this spot should be good. Okay. So, clamp it slightly. Now, we have to put in, first we zero the force dial. Now, we put in a preload of 10 kilograms. I have to look through the viewfinder here, so this should be good. Okay. So that's the preload of 10 kilograms on the indenture. Now it is seated on the surface. Next, we have to zero the depth dial. I hope this doesn't look too stupid on camera, but I have to look in an oblique way onto the indicators. Alright, so preload is on. Depth measurement is zeroed, and now we put in the test load of 150 kilopounds. I'll do this with this Allen key here. So that's 100 and 150. You already see on the second indicator that we sunk into the surface already, of course. So 150 kilopounds, that is. Now we have a holding time of 4 seconds as per ISO standard for Rockwell measurements. And now we relax the load on the indenter back down to the preload of 10 kilograms, or 10 kilopounds. Ideally, this should be done very smoothly, the increase in force and the decrease in force, but I have to film here as well, so back down to the preload, and now we can read the value here. We have to use the outer scale on the sticker ring, on the white ring. So that says we are on 54 Rockwell, and the plate has 54.7. Alright, so let's repeat that and see where we are with the second try. Alright, so first try with the 54.7 plate, result was 54, so that's below 1% of error. Given that the Rockwell scale, Rockwell C scale goes from ranges from 0 to 100. Okay, so let's make a second indent. Oops. The spot should be good. Okay. So the force dial is zeroed. Alright. Then we put in the preload of 10 kilopounds. Should be good. We zero the depth dial. Alright. Then we apply the 150 kilopounds test load again. So that's 100. And $150. 4 seconds holding time. And down we go again to the preload. So back down to 10. And our result is, remember we're on the outer scale of the white ring, and our result is, I would say, quite spot on. It's a bit more than 54.7. The plate has again 54.7, and so that's not too bad. Alright, so far as the Rockwell cone method is concerned, the Rockwell ball method for the softer materials works just the same. You only use a different indenter with a tungsten carbide ball of 1/16 of an inch diameter, and you use the inner scale of the white ring. But the procedure is the same, only the total load is not 150 kilopounds but 100. So you see, these two methods with their definitions of measuring the depth are very convenient if you have to do work in the field or away from your home shop where you have all your equipment, because you only need this tool and nothing else. You can directly read the result and don't have to do any computations or measurements on another instrument. So far so good. The only problem with the Rockwell hardness values or the Rockwell testing procedures is that they do not translate proportionately into material strength. So twice the Rockwell hardness does not necessarily mean twice the material strength. There is a certain nonlinearity. If you're interested in material strength and use there are lookup tables available to translate from Rockwell to strength, then you should be fine. However, just for the gut feeling and for shop use, it may be misleading to just use Rockwell if you're interested in the material strength. So the other most common hardness testing methods, which are the Brinell and the Vickers hardness tests, they get rid of this problem by not measuring the depth with which the indenter sinks into the material, but rather we measure the size of the indent, then compute the surface area of the indent, and compute the ratio between indentation force and surface area of the indent. And this is more related to material strength than what we do with the Rockwell tests. So, long story short, let's see how that goes. So in essence, we don't have to mess with preload, we don't have to mess with that indicator at all. That's why we pull it back out so that it doesn't even touch the sample. So that should be good. And we only apply a certain indentation load, then take out the sample and measure the size of the indent. In this video here, I'm going to show you how we measure, or how I measure the indent in my profile projector. This can be done in any measurement microscope. Usually with the stationary hardness testing machines, the microscope is built into the machine as well. But I want to show you how this is done with this setup here. So let's change the indenter first. I will show you a Vickers hardness test. Vickers uses an indenter that is shaped like a pyramid. There is a diamond tipped pyramid here on the indenter. And the nice thing about this pyramid shape is that the indentation is a square. No matter how deep it sinks, it's always a square. The Brinell test is different, it uses a ball, and the problem with that in comparison to Vickers is the deeper it sinks, the sharper are the edges. But if you have only very shallow indents, then the edges that you have to measure the size of the indent. Then the edges that highlight the indent are very hard to see, or maybe very hard to see. With Vickers, that's not a problem. It's always a square, and that's why Vickers is the most versatile hardness testing method, because it has the least disadvantages in comparison to the other methods. So let's use this Vickers comparison plate here. This one has a 302 Vickers hardness. So let's find us a good spot. All right, clamp it, and now we apply a certain load. Now with Vickers there are various loads defined that you can use in the standard. Also the result should be quite independent of the load that you use. That's the nice thing, because this is quite related to material strength and not as linear as Rockwell. So with different loads we should achieve the same result for the hardness. So let's see about that. Let's use 50 kilopons of load. Good practice in hardness testing is to always use the largest load that you can. In Rockwell they are already specified, but in Vickers and Brinell to always use the largest loads that you can. Of course then the indents get larger and you have to know what you can get away with without having to scrap the workpiece. But it's beneficial to have large indents, because then the errors and the result scatter get way smaller than with small indents. So okay, we said we want to use 50 kilopons. Let's put that on. So that's 50. Then the Vickers test is defined with a holding time for the load of 10 to 15 seconds. So be patient with me. I guess that's it. And now, alright, test is, or indentation is done. Now let me take it out, and I want to take it out that you can see where the indent is. I'll mark it and then we go to the profile projector and measure it. I just want to avoid that you can say, Alex, you're measuring another indent than the one you made on camera. So it's the one in the center here. Let me get the pen. So it's this one here. Okay, let's check the size of this one. Alright guys, so here is the marked indent on the profile projector screen. We're currently at 5 times magnification. So our indent that we want to measure is in the center of the screen, so I'll go to 100 times magnification now, and this should be this particular indent. Sorry, I have to get my hand just for a second. Yeah, focus is good. Okay, so and now you see the indent is a nice square, or almost a square. Here we see this, these are some plastic effects that cause the square to deviate from the diamond, but that doesn't matter in the test. So next we want to measure the length from one corner to the other and do the same on the second set, and then we want to make the average of that and use that for computation. So first thing, we must align the diagonals of the square with the measuring grid, and I'll try to do so by turning the screen grid. Yeah, that should be it. And now we have to read the length, and we are on 100 times magnification. That means we can use this scale here, where this is 1, and so our indent has so our indent has 0.553, I would say, millimeters, and our second measurement is this length from here to there, and this is 0.549, I would say. So 0.553 and 0.549 millimeters. Alright, so that was 0.549, I believe, and 0.553, if my brain is not mistaken. Okay, so the average value of these two is 0.551 millimeters, average diagonal length. Now the formula for the Vickers hardness to compute it is 2 times the load that we applied during indentation times the cosine of 22 degrees. This has to do with that pyramid shape, divided by the average diagonal length squared. So in our case, this is, let me see, hope you can see the calculator, 2 times 50 kilopounds times cosine 22 degrees divided by 0.551 squared, right? And that equals 305.4 Vickers. HV50 is the unit that we have to specify, because we used a testing load of 50 kilopounds. And considering that this comparison plate has a rated hardness of 302 Vickers, and keeping in mind that the Vickers scale ranges from 0 up to above 1,000, then this error is really quite alright for me, or for my purposes. When you have smaller, or when you use smaller loads, the errors might get as large as, I don't know, plus or minus 50 Vickers, even with the best testing machines. This has several reasons. For example, you may just, if the indentation is really small, you may just be in one grain of the material, where the direction has a significant influence on the indent and stuff like that. So this is a really good result, I think. And yeah, that was the Vickers test. The Brinell test works absolutely the same. You just use another indenter, not the pyramid, but a ball indenter, and you use a different formula to compute the Brinell hardness, but in essence it's the same. I personally don't like using the Brinell hardness so much, because you also have to check that the indentation size is within a certain range of the ball diameter. In other words, that the indentation is not too flat and not too large, with the extreme case being sinking beyond the equator of the ball. And this has to be checked always when you do the Brinell test, and this is something that you don't have to do with the Vickers test. This is why I like, or why I consider the Vickers hardness test the most universal one, even if it's not the most established one, but the most universal one in my opinion. Alright guys, this wraps it up. Thanks a lot for your interest in this video. I appreciate your time. I hope you find the one or the other thing useful, and see you next time.